A team of Korean researchers are working to develop a way to harness energy using seawater. Our Kim Yo-sun introduces to us this new type of battery that relies on an abundant and readily available source.
They said the future of energy would be lithium. They were wrong. In a quiet lab, scientists have unlocked something extraordinary. An unassuming battery made not from rare earth metals, but from salt water.
Doesn't use the expensive raw materials. There's no cobalt, there's no copper, there's no lithium. We're looking at between 24 to 32% less expensive for the bill of materials for sodium ion compared to lithium ion.
No mining scars, no toxic waste, just the ocean's abundance turned into power. This breakthrough could end our dependence on dangerous supply chains and rewrite the rules of global energy. This video explores an increasingly important question in the renewable energy sector. How can we store large amounts of energy in a way that's cost-effective, scalable, and reliable? There's no shortage of ideas when it comes to storing energy from renewable sources like wind and solar. Engineers, scientists, and companies are experimenting with a wide range of battery chemistries, mechanical systems, and thermal storage techniques. However, many of the promising solutions run into the same roadblock. The raw materials they rely on are expensive, limited in supply, or both. Lithium-ion batteries, for example, are widely used in electric vehicles, portable electronics, and increasingly for grid-scale storage. They are powerful, relatively compact, and familiar. But lithium is not the most abundant resource, and its mining and processing can be costly and environmentally challenging. Beyond that, lithium-ion cells involve other elements like cobalt or nickel, which face their own supply issues and price swings. This raises concerns about whether relying on lithium-ion as the main long-term storage solution for the grid is sustainable or affordable in the future. Other types of flow batteries, a category of rechargeable battery where energy is stored in liquid electrolytes, have gained attention as alternatives. In particular, vanadium redox flow batteries, or VRFBs, are considered a mature and proven type of flow battery. They work by exploiting vanadium's ability to exist in multiple oxidation states, allowing both electrolytes in the system to be based on the same element, which reduces cross-contamination and extends battery life. While this is technically impressive and provides long service life, vanadium has its own economic problem. The price of vanadium is notoriously volatile because it's heavily tied to the steel industry, where it's used as an alloying agent. When steel demand rises, so does vanadium demand, and its cost. Research has shown that for vanadium flow batteries, the cost of the electrolyte alone can make up a very large proportion of the total system cost. A 2016 study estimated that it could represent nearly 60% of the overall cost. More recent findings from the University of California, Irvine in 2021 suggested this share could be as high as 80%. For a technology that's meant to provide affordable grid-scale storage, these numbers present a significant barrier to widespread deployment. Given these challenges, some innovators are looking to elements that are far more common, easy to source, and inexpensive. One particularly interesting candidate is sodium chloride, ordinary table salt. Sodium is one of the most abundant elements in the Earth's crust and oceans, and chlorine is also widely available. Together, they form sodium chloride, which can be extracted from seawater, mined as rock salt, or obtained from other industrial processes. The idea of using salt in an energy storage system is not new in a general sense. Sodium-based batteries, including sodium-ion and molten salt designs, have been studied and deployed in various forms. However, applying sodium chloride in a redox flow battery is a more recent development. A US-based company called Infinity Turbine has developed a system called the Cell Gen X flow battery, which they claim could bring down costs substantially by using this abundant material in a straightforward design. At its core, the Cell Gen X works like other redox flow batteries. There are two tanks containing different liquid electrolytes. During charging, electrons move in one direction through the system, and during discharge, they move back. In this case, one tank contains chlorine gas dissolved into a proprietary electrolyte. while the other contains a mixture of sodium chloride and water. The design avoids the use of expensive vanadium or complex synthetic chemicals, relying instead on substances that are inexpensive and easy to obtain. One of the advantages claimed by Infinity Turbine is that their electrolyte materials can cost under $5 per kilowatt hour, a fraction of what vanadium-based systems require. If accurate, this difference in material costs could make a substantial impact on the economics of large-scale storage, especially for projects that require many megawatt-hours of capacity. The availability of sodium chloride also reduces dependence on specific mining operations or geopolitical supply chains. Salt can come from multiple sources, including ocean water, brine from geothermal plants, or even cooling ponds at power plants. This flexibility could make it easier to deploy such batteries in many different regions without the supply bottlenecks that affect other chemistries. Understanding why this matters requires a look at the broader challenge facing renewable energy systems. Solar panels and wind turbines generate electricity when the sun is shining and the wind is blowing, but not necessarily when demand is highest. This mismatch between supply and demand is often referred to as intermittency. Without ways to store excess energy when it's plentiful and release it when it's scarce, renewable generation can't fully replace fossil fuel plants that provide consistent output. There's also the issue of curtailment. At times, renewable generators produce more power than the grid can handle or than is needed at that moment. Without storage, this extra energy is wasted. In some regions, operators even pay wind or solar farms to shut down temporarily when supply outstrips demand. Long-duration, affordable storage would allow this excess to be captured and used later, reducing waste and lowering overall costs. Lithium-ion batteries can address some of these issues, but aren't always the best fit for long-duration storage. They are well suited for shorter periods, from minutes to a few hours, but scaling them up to store energy for 8, 10, or 12 hours or more becomes expensive and introduces safety considerations. Flow batteries, by contrast, can be scaled more easily by increasing the size of their electrolyte tanks, allowing for much longer discharge durations without drastically increasing the complexity of the system. The key challenge for flow batteries has been finding chemistries that combine affordability, durability, and acceptable performance. Vanadium works well in terms of lifespan and efficiency, but its cost remains high. By turning to sodium chloride, one of the most common and cheapest chemical compounds available, developers hope to make flow batteries economically viable for widespread use. The Cell Gen X concept is not the only salt-based approach being explored, but it serves as a clear example of how thinking beyond the traditional battery materials could change the market. If such systems can deliver on their cost and performance claims, they might open the door to renewable energy storage that's both abundant and affordable, without relying on scarce resources. One of the most important measures for any energy storage technology is its cost relative to performance. While the chemical processes inside different battery types can be complex, the numbers often determine whether a system is adopted at scale. In the case of sodium chloride flow batteries, one of the biggest selling points is how inexpensive the electrolyte materials are compared to those used in conventional vanadium-based systems. Estimates from the U.S. Department of Energy suggest that vanadium redox flow battery electrolytes can cost anywhere from $105 to $180 per kilowatt hour, depending on the grade and processing method of the vanadium used. By contrast, Infinity Turbine's Cell Gen X battery claims its electrolytes can be produced for less than $5 per kilowatt hour. That price gap is substantial. In large grid-scale installations, the electrolyte volume required can be enormous, and a difference of over $100 per kilowatt-hour can amount to millions in savings. For utilities and developers looking to deploy long-duration storage across hundreds of megawatt-hours, lower upfront costs make the technology far more appealing and can help shorten the time it takes for a project to become cost-effective. The Cell Gen X also aims to keep costs down in other ways. One notable feature is its membrane-free design. Most redox flow batteries include a membrane that separates the two sides of the system, allowing ions to pass while keeping the different electrolytes from mixing too quickly. While effective, these membranes are not cheap. A study in 2014 found that ion exchange membranes could cost several times more than the plates and electrodes used in the same battery. Even with expected reductions in membrane costs over time, they remain a significant part of the total bill. Infinity Turbine's approach avoids this expense entirely. Instead of using a physical barrier, the Cell Gen X design relies on the natural immiscibility of its two liquid electrolytes to keep them separated, similar to how oil and water remain in distinct layers when combined. This removes not only the initial purchase cost of the membrane but also ongoing maintenance and replacement expenses, as membranes can degrade over time and affect performance. From a technical standpoint, the company states that their saltwater flow battery achieves a round-trip efficiency. Round-trip efficiency refers to the proportion of energy that can be retrieved from a battery compared to what was put in during charging. A high figure indicates that relatively little energy is lost during storage and retrieval. At 91%, this places the Cell Gen X in the same range as many lithium-ion chemistries, which often achieve efficiencies between 85 and 95% under standard conditions. Energy density, the amount of energy stored per unit volume, for the Cell Gen X is listed at around 125.7 watt-hours per liter. This is significantly lower than most lithium-ion batteries, which can range from roughly 210 watt-hours per liter for lithium iron phosphate (LFP) cells, up to about 600 watt-hours per liter for high-performance lithium, nickel, manganese, cobalt (NMC) designs. A lower energy density means that for the same amount of stored energy, a sodium chloride flow battery will require more space than a lithium-ion system. For stationary, large-scale storage, where footprint is less of a concern than in mobile applications like electric vehicles, this is not necessarily a problem, but it does influence installation planning. Beyond standard storage functions, Infinity Turbine has proposed additional uses for its technology. One idea is integrating the battery into a desalination system. Because the battery already involves the movement of ions between two electrolytes, the process could be adapted so that it simultaneously generates electricity and produces fresh water from salt water. This could be particularly useful for applications such as cruise ships, cargo vessels, island communities, or remote coastal installations, where both electricity and fresh water are needed, and space for separate systems is limited. Another potential application under development is using the Cell Gen X process to produce graphene. Graphene is a form of carbon arranged in a single layer of atoms, known for its exceptional strength, conductivity, and range of potential uses in electronics, composites, and other advanced materials. Infinity Turbine claims that by adapting its battery technology, it could produce graphene at a much lower cost than current commercial methods. While the average market price of graphene can range from $100 to $400 per gram, the company suggests its process could reduce this to just over $1 per gram. It is important to note, however, that these figures are projections and the approach still needs to be proven at scale. Salt-based flow battery development is not limited to Infinity Turbine. Another American company, ESS, has been advancing its own version of the technology, using iron salts dissolved in water as the electrolyte. In early 2023, ESS announced a collaboration with the Turlock Irrigation District in California as part of Project Nexus, an initiative to install solar panels over irrigation canals. The ESS batteries will provide long-duration energy storage for the project, allowing solar power to be stored during the day and released later when needed. The goal is to complete construction by 2024. ESS is also working with the Sacramento Municipal Utility District to install iron flow battery systems in California. Their design shares some similarities with the Cell Gen X in that it uses abundant, low-cost materials, but instead of sodium chloride, it employs iron chloride. This choice offers some distinct benefits. Iron is one of the most abundant elements in the Earth's crust, with a concentration of about 52,000 parts per million, compared to roughly 138 parts per million for vanadium. This makes iron not only plentiful, but also inexpensive. Another advantage is that the ferrous chloride used in ESS batteries can be sourced from waste products in the steel-making process. In particular, a byproduct known as pickle liquor, a solution used to clean steel during manufacturing, can be processed to recover the iron salts needed for the battery. This creates an opportunity for industrial recycling, turning waste into a valuable component for energy storage. By using such common and non-toxic materials, ESS aims to avoid many of the safety concerns that come with vanadium or other hazardous electrolytes. The company notes that its iron flow batteries do not require hazardous materials permits for transportation, installation, or disposal, and they also avoid the need for complex fire suppression systems. Since the electrolyte is water-based and non-flammable, the risk of thermal runaway, a dangerous overheating reaction that can occur in lithium-ion cells, is virtually eliminated. While ESS and Infinity Turbine are pursuing different chemistries, both approaches are built on the same underlying principle: replace expensive, rare or hazardous materials with cheap, abundant, and safe alternatives, while preserving the flexibility and scalability of the flow battery design. This approach could make long-duration storage far more viable for a wider range of projects, from large utility installations to smaller community systems. When comparing these salt-based designs to lithium-ion solutions, certain trade-offs stand out. Lithium-ion still offers higher energy density, which is important where space is at a premium, but it typically has a shorter lifespan in terms of the number of charge and discharge cycles. Flow batteries can last decades with minimal capacity loss, provided their components are maintained. This is partly because the electrolyte is stored in tanks and does not degrade in the same way as solid electrodes in conventional batteries. The promise of low-cost electrolytes, simplified design, and safe operation makes saltwater and iron flow batteries an attractive proposition. However, like any emerging technology, they will need to prove themselves through consistent, reliable operation in real-world conditions. Large-scale deployment will require not just good performance, but also competitive total costs over the system's lifetime, ease of installation, and compatibility with existing grid infrastructure. Iron-based electrolytes, such as those used by ESS, present a strong contrast. Iron is far more abundant than vanadium. Estimates put its presence in the Earth's crust at over 50,000 parts per million, while vanadium is around 138 parts per million. This abundance translates directly into cost advantages. Iron salts are inexpensive, widely available, and relatively easy to source from a range of suppliers. In fact, iron can often be recovered as a byproduct of other industrial processes, such as steel manufacturing. This reduces the need for dedicated mining or processing operations, and can also help reduce waste from those industries. From an environmental and safety standpoint, iron and sodium chloride electrolytes share another key benefit. They are non-toxic and water-based. Many vanadium compounds, particularly vanadium oxides, are toxic and require special handling. While vanadium-based flow batteries can be operated safely with the right procedures, the safety requirements add to the complexity and cost of install, transport, and disposal. In contrast, iron and saltwater systems avoid these hazards, meaning they generally do not require hazardous materials permits, extensive fire suppression measures, or specialized disposal plans at the end of their life. Another major factor is the operational life of the battery. Lithium-ion batteries, which dominate in many applications today, typically last for around 1,000 to 2,000 full charge-discharge cycles before their capacity degrades significantly. This is fine for uses where the battery is replaced after several years, such as in consumer electronics or electric vehicles, but less ideal for large infrastructure that is expected to operate for decades. Flow batteries, including those using iron or sodium chloride, can achieve far greater cycle life. ESS, for example, claims its iron flow systems can handle over 20,000 cycles, which would support daily cycling for more than 50 years in theory, though other components of the system may need maintenance or replacement sooner. Infinity Turbine's CellGen X is also designed for a lifespan of around 25 years, which is in line with the expected life of many renewable generation assets, such as wind turbines and solar farms. The duration of energy storage is another area where these technologies stand out. Lithium-ion batteries are generally most cost-effective for storage durations of 4 hours or less. Beyond that point, the cost per kilowatt-hour of capacity rises sharply because more battery modules must be added. Flow batteries, on the other hand, can be scaled for longer durations, simply by increasing the size of the electrolyte tanks. This makes them better suited for long-duration applications, such as storing solar energy generated during the day for use overnight or balancing wind output across multiple days. ESS has stated that its iron flow batteries remain cheaper than lithium-ion for durations beyond 4 hours and can be configured for up to 12 hours of continuous output. For some grid applications, this flexibility can be a significant advantage, allowing operators to better match supply with fluctuating demand without overbuilding capacity. This could also help reduce reliance on fossil fuel backup plants, which are often kept on standby to cover gaps in renewable generation. When evaluating new energy storage options, it's also important to recognize that no single technology is likely to meet all needs. Electricity systems are complex, and different applications require different characteristics. For instance, frequency regulation, the rapid adjustment of power supply to keep the grid stable, demands high power output for short periods. Lithium-ion batteries are well suited for this because of their fast response and high energy density. In contrast, storing excess solar energy for use over a long winter night may require hours of continuous output at a steady rate, which plays to the strengths of flow batteries. This is why many experts argue for a portfolio approach to energy storage. Pumped hydro, compressed air, lithium-ion, sodium-ion, vanadium flow, iron flow, and other chemistries all have potential roles, and the best choice depends on the specific application, location, and economic conditions. Saltwater and iron-based flow batteries may not replace lithium-ion in electric vehicles or portable electronics, but they could become a vital part of stationary storage infrastructure, especially in areas where long-duration storage is needed, and safety or cost constraints limit other options. In addition to technical performance and cost, scalability is a factor that determines how far a technology can go in meeting global storage needs. Materials availability is critical here. Lithium, cobalt, and vanadium all face some degree of supply constraint, with production concentrated in a limited number of countries. This can create vulnerabilities to geopolitical tensions, export restrictions, or trade disputes. Sodium, chlorine, and iron, on the other hand, are widely distributed and produced in large volumes around the world. This reduces the risk of supply shortages and price spikes, making it easier to scale production without running into resource bottlenecks. Environmental considerations also come into play. Extracting lithium, cobalt, and vanadium often involves intensive mining processes that can have significant ecological impacts. Using byproducts from existing industrial processes, such as steel manufacturing waste for iron electrolytes, can reduce the need for new extraction and help make the overall supply chain more sustainable. Similarly, sodium chloride can be sourced from seawater or brine, with relatively low environmental impact compared to mining operations. As with any emerging technology, the long-term success of saltwater and iron flow batteries will depend on their ability to prove themselves in real-world conditions. Laboratory results and pilot projects are encouraging, but utility-scale deployments are the real test. Systems need to operate reliably under varying conditions, integrate smoothly with existing grid infrastructure, and deliver the promised cost savings over their full lifespan. Maintenance requirements, durability of components, and operational flexibility will all be closely scrutinized. Some of these systems are already being put to the test. The projects in California involving ESS are an opportunity to see how iron flow batteries perform alongside large solar installations in a real grid environment. Similarly, if infinity turbines desalination and graphene production concepts progress beyond the development stage, they could demonstrate the value of multifunctional energy systems that do more than just store electricity. The appeal of these technologies lies in their combination of low-cost materials, inherent safety, and scalability. If they can deliver on these promises, they could help enable a more resilient and affordable renewable energy system. This is especially relevant as countries aim to increase the share of renewables in their energy mix. Intermittency remains a major challenge, and long-duration storage is a key part of the solution. The broader lesson is that there is unlikely to be a single. In the race to build the perfect battery, the needs of the grid vary widely depending on time of day, season, geography, and the mix of generation sources. A combination of storage technologies, each optimized for different tasks, is likely to be the most effective approach. In that mix, saltwater and iron flow batteries could find a strong position, particularly where their unique strengths align with the demands of the application.